Okay, let's go ahead and start on this. The first thing we want to do is create this single replacement reaction. I'm sorry about the error here with the iron. I posted that last night. This shouldn't say iron, it should say magnesium. It was a typo, yeah. So we start off with magnesium and hydrobromic acid. And it's a single replacement reaction. So what happens? No, the H cannot go onto the Mg. Why? Because they're both positively charged. So the magnesium and the bromine come together. So I'll have a magnesium with two bromines. Because magnesium's charge is +2 and bromine's charge is -1. And that allows me with an H. But it's not just H, is it? It has to be H2 because hydrogen is one of the diatomics. Okay. What do I need to do now?
So the only thing, you know they go together is because of the charges. That's the only reason.
Yeah, it's the only reason. Just like when we were naming them, you know what the formula was because it was all about the charges. Yeah.
So the same goes with solubility rules. Like like they separate because one of them wants to separate, come together because of the charge as well.
They would come together.
Like how do you know which one's arranged to the other side with food?
Well, I said this was a single replacement reaction, so you needed.
I guess I'm getting ahead of myself on the other.
So on the next one, yeah. Well, we'll get to it, but there's only one way to do it because of the charges. You're right. So there's my formula, or there's my reaction. What else do I need to do? There needs to be a 2 right here, and then I can balance out the hydrogens and the bromines. And then the magnesiums I only need 1 on each side. Okay. So I've got 125 grams of magnesium, and I've got 275 grams of HBr. Let's see. So the magnesium's mass is 24.305 grams of magnesium for 1 mole of magnesium. And the hydrobromic acid is 80.911 grams of hydrobromic acid for 1 mole of hydrobromic acid. So you do exactly the same thing with each of these. I start off with whatever I was given, and then I use the molar mass off of the periodic table. What do we do next? Look at the balanced chemical equation. Okay. I need to know what it is that I'm looking for, and in this case, what I want to know is what's left in the container after the reaction's finished. So, what do I need to think about to answer this question? I have to know which one runs out first. So to answer that question, I have to take both of these first 2 railroad tracks to the same product. So it doesn't matter which one. So I'm just going to pick the hydrogen just because I'm going to pick the hydrogen. So then it's moles of magnesium here, just like it's moles of hydrobromic acid here. And then I'm going to go to the hydrogen. So moles of hydrogen and moles of hydrogen. And it's 1 mole of hydrogen for both of these. And the magnesium, it's 1. And for the hydrobromic acid, it's 2. Where did those numbers come from? Yeah, just look at the balanced chemical equation, and the only thing that's got a number other than 1 is the HBr, so I throw a 2 in front of the HBr. So I can cancel out my mole part, so moles of magnesium, moles of magnesium, moles of hydrobromic acid, moles of hydrobromic acid, and then I can just keep going on with this. And so it'll be 1 mole of H2 and 1 mole of H2, and then it's 2.0159 grams of H2, 2.0159 grams of H2. All right, and I got, let's see, 125 divided by 24.305 times 2.0159. So I've got 10.4 grams of hydrogen gas, 275 divided by 80.911 divided by 2 times 2.0159. And I get 3.43 grams of hydrogen gas. All right, what did I just learn? Negative. The hydrobromic acid is going to run out first. Why? Not because it's less. What's less? So tell me what happens the instant I have made 3.43 grams of hydrogen. What has happened? Hydrobromic acid is gone. So can I make 10.4 grams of hydrogen? Nope. So I know that there is 0 grams of hydrobromic acid in this container when the reaction is done. I know there's 3.43 grams of hydrogen gas in the container. I know there's going to be some leftover magnesium, and I know that there's going to be magnesium bromide made. So we're going to have to do more railroad track. So I don't care about the magnesium amount anymore because that's not going to tell me information. So I'll go ahead and do 275 of HBr, 1 mole HBr, 80.911 grams of HBr, and 2 mole HBr. Okay, so it looks just like the one right above it because I'm trying to figure out how much of the magnesium bromide I'm going to make with this. So I'm going to put 1 mole magnesium bromide up top, and then 1 mole, 1 mole magnesium bromide. And then it's 184.113 grams of MgBr2. All right, so I've got 184.113, and this is 313 grams of MgBr2. So I know I've got this much magnesium bromide made in the container. I want to know one more piece of information though. What is it? Well, that's 0. How much magnesium is left, right? The hydrobromic acid ran out. So there's 2 ways I could do it. I could run another railroad track, or I can look at this and say, I put 275 grams and 125 grams of stuff in. So I put 400 grams of reactant in. You okay with that? What's the mass of the stuff in the container when this is finished? It's 400 grams. The mass has to stay the same. I didn't do anything with the atoms except changed partners, right? So I have to still have 400 grams. And what I know is I have 0 grams of HBr. I know I've got 3.43 grams of hydrogen, and I've got 313 grams of MgBr2. So 313 plus 3.43, and this is 316 grams of product. So how much magnesium is left? 84 grams of leftover magnesium. How do I know that? Well, I know I just made this much new stuff, and I completely ran out of hydrobromic acid, so the rest of the 400 grams must be my leftover magnesium. That sound good? Okay. Alma, what's up?
So I guess I was kind of confused on how they come back together. Why is that absolutely separate? Like I don't know. Is it just because it's charged? Okay.
That's it.
Sure. Like how do you know which one goes to which?
So I know this thing is positive 2 and this thing is a minus 1 just by looking at the table, and I know this is a plus 1 and I know this is a minus 1. So what could react? Could the bromine react with the nitrate? No, they're both negative. Can the silver react with the magnesium? No, can't do that either because they're both positive. So I either leave it as it is or I do what? I switch either the cations or the anions. It gives me the same thing. So what kind of reaction is this? This is a double replacement. These are always going to just be double replacement reactions. So if I do a double replacement reaction, that means I need a magnesium reacting with a nitrate, and I need a silver reacting with a bromine. So what's wrong with what I wrote here for the magnesium nitrate? The charge is imbalanced, right? So to do that, I'm going to need 2 nitrates because the nitrates are minus 1. So now that magnesium nitrate, that's correct. So when I just did that, I added another nitrate to the whole problem. So what do I need to do to the other side of the equation? I'm going to need to put a 2 right here. So now I have 2 nitrates. But that did what for me? Gave me 2 silvers. So I need to put a 2 in front of this, which was really good because I needed to put a 2 in front of that anyway. For what reason? Because I started off with 2 bromines. So there's my reaction. To do these reactions, the only way that this reaction is going to actually react is if these things are in water. So this little section in the notes was titled "Reactions in Water." And what are magnesium bromide and silver nitrate? What kind of compounds are those? They're ionic. What's another name for an ionic compound? Really easy name. Salt. If you took 2 salts and mixed them together, would anything happen? No. They're solid. They're stuck to the things they already want to be stuck to. So if I need to get the cation to react with a different anion, what's the first thing I have to do? I got to put them in water so they separate, so then they can recombine in a different orientation. So this has to be aqueous. This has to be aqueous. And then once I've done that, I have 2 compounds that can be aqueous. I look to see what happens when I swap their partners, and I check the solubility rules. So what happens over here with the magnesium nitrate? It never actually came together. I'm only writing it in this molecular equation because it's faster. But it never actually came together. That's what that AQ means. But what about the silver bromide? Bromide wants to be insoluble, but bromide wants to be soluble, but silver wants to be insoluble, and the silver rule is above the bromine rule, so silver wins. So this forms a solid, and what do we call that? That's the precipitate in the reaction. So the chemical reaction that happened is I made silver bromide. So okay, so what do I do with the full ionic equation? What does aqueous mean? More. It means, for a salt, it means the thing's actually been disassembled. So what's wrong with me writing this here, this MgBr2? they're really not connected. It's very, very misleading. But I wrote AQ, so that's telling you that I had a salt and they were stuck together, and I put it into some water, and I told you that because it says AQ. And because bromine's there, it's soluble, so what did it do? Separated into the 3 particles. So when this happens, I've got a magnesium that has a +2 charge, and I have 2 chlorides with a minus charge. Bromides with a minus charge. I don't know why I said that. 2 bromides. I know bromines are a diatomic, but why are they not? Why isn't it a subscripted Br2? These aren't atoms. What is this bromine? It's an ion. It's charged. So it doesn't behave like an atom because it's not an atom. So I don't have a Br that's connected to another Br. That's what this means. These 2 Brs are connected to this magnesium. This is 2 separate Brs. They're independently floating through the water, not connected to each other. And then that magnesium is floating as well. So then this guy gets a state of AQ, and this guy gets a state of AQ, and then we just move on with this. I have 2 silvers that are aqueous, and I have 2 nitrates that are aqueous, and then an arrow. And then on the other side, I've got a magnesium with a +2 charge that's aqueous, and I have 2 nitrates that are aqueous, and I have 2 silver bromides that are still stuck together. How come I didn't separate out the silver bromide? It really is connected, and I know that because up top I wrote down solid for that. And I knew that because of the solubility rules. So the difference between the full ionic and the net ionic is what? The spectator ion. So this magnesium right here with the charge on it looks exactly like this magnesium right here. So that means that magnesium is a spectator ion. And this nitrate looks exactly like this nitrate right here. So that is also a spectator ion. So what I do is I write everything that I didn't highlight. And so the chemical reaction was a silver that's aqueous plus a bromine that's aqueous makes silver bromide that's a solid. Does it matter if I write the silver before the bromine? No. I mean on the left-hand side. It does matter on the right-hand side. Does it matter that I didn't write 2's in front of all of them? No, because you can just divide through by 2. If you put them up there, that's fine. If you swap the silver ion and the bromine ion's position, that's fine. It's just doesn't matter.
So why don't you put the 2?
You can, but if I did, I'd put a 2 right here, and a 2 right here, and a 2 right here. So mathematically, what would you do? You'd reduce it, and you divide everything by 2. But if you put them, I mean, it's not technically wrong. It's just like you'd upset a math teacher. Okay, last one here. I want you to explain exactly how you're going to make this. The people who had lab on Tuesday had a distinct advantage over the people who have lab today. So, to make a solution, you have several things to do. And we talked about this in class, but this is what you need to do. I need to figure out exactly how many grams of potassium bromide I need. Why am I calculating grams when this is a moles per liter thing? I can't measure out moles. I can only measure out grams. So this is us counting how many particles I want in terms of grams to calculate out how many moles I'm going to end up with. So first thing I need to do is calculate how many moles. So we're going to do that in a second. What's the next thing you do? After I know how many grams I need. You're going to add that mass of solute to a volumetric flask. Like 2/3 fill. with water and mix. Fill near line. Fill to line with dropper. So that's exactly how you're going to make this solution. So let's calculate how many grams of the potassium bromide I need. So it's what I have. The piece of information that I have here is I've got this 500 milliliters of solution that I need. I know I want the solution to be this concentrated. What's that capital M stand for? Moles over liters. I need grams though. So I don't have any grams up here. Where am I going to get the gram unit from? I'm going to get it from the periodic table. So if I look at the periodic table, I'm going to find out that potassium bromide's mass is 119.0023 grams of KBr per 1 mole. Okay, so since I'm looking for grams, I'm just going to go ahead and start with that. 119.0023 grams KBr, 1 mole KBr. Okay, so I want grams, but it came with moles, so I need to get rid of the mole part. So how do I get rid of the moles KBr? Oh, was I given something that had moles in it? So I'm going to go with 2.5 moles of KBr per 1 liter of solution. Sorry, just leave it at 1 liter. And when I do that, I'm going to go ahead and cancel out my moles of KBr. But now I have a liter unit, and I don't want the liter unit. So what do I do? Take that 500 milliliters and turn it into liters. So I'll just put 500 milliliters up here. That won't cancel out, but I can cancel it out by saying 1,000 milliliters is 1 liter. And so then when I do that, I get the liters to cancel out and the milliliters to cancel out. The only unit I have left is grams of KBr. And then if I do this math, I get 119.0023 times 2.5 times 0.5. I get 149 grams KBr. I guess that works out to be 150 grams of KBr with sig figs. So I take 150 grams of KBr, throw it into a vol flask, that's 500 milliliters. Fill it like 2/3 of the way, shake it, fill it near the line, and then fill it to the line with a dropper.